Trusses are versatile structural components known for their efficiency in carrying loads over long spans while minimizing material usage. Their applications extend across various industries and structures, making them a crucial element in modern engineering and construction. Trusses are commonly used to support the roof of various buildings, including houses, commercial structures, and industrial facilities. They provide stability and help distribute the weight of the roof evenly. Truss bridges are a classic example of truss structures. The triangular arrangement of members in trusses makes them ideal for spanning long distances and supporting the weight of vehicles and pedestrians on bridges. Today, you will learn what trusses actually are and how do we analyze them.
Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life.
In today's lecture, I would like to cover a very important topic, which is trusses, pin-jointed trusses. By the end of today's lecture, you'll be able to learn how to find out forces in a truss. And I'll be able to tell you that where do we use trusses and why do we use the trusses. It is very important to understand how do we work out these member forces. And in some of the members of a truss, we see that how can we find out forces without even calculation, just by looking at those members to see that what member forces they can develop. Pin jointed frames. Now, what is the difference between pin jointed frames and rigidly jointed frames? And I would say there is one key difference. And what is that key difference? If I have two frames here, one is pin jointed, other is rigidly jointed frame. This is pin jointed frame and this is rigid. The key thing is that pin jointed frames, and trusses is one of the example, they carry only axial forces. They carry tension and compression. And why do they do that? Because I have these pins over here, this frame allows rotation. So when rotation is allowed, moment does not develop at the joints. And when there is no moment, certainly there is no shear. And that leaves us with axial forces, which are tension and compression. And other thing, the loading in pin jointed structures is applied at the pins. So it could be here, it could be here. On the other hand, in case of rigidly jointed structures, you could have UDL and you could have load applied to the joints. And in rigidly jointed structures, joints are rigid. It can develop not only moment, but shear as well. What would be learning outcomes of this lecture? You will at least be able to determine the external and internal forces on pin jointed frames. It means that you will be able to find the member forces, in other words, in pin jointed frames. And the method that we are going to use is method of joints, method of resolution of forces at joints to solve a pin jointed structure, a pin jointed frame. Now, pin jointed frames and trusses. Trusses are part of pin jointed frames. These are very important structures. These are used to support long spans, especially trusses. Trusses can span up to 100 meters and they can transfer loading efficiently. They are used in roof structures, road and rail bridges to transfer loading. This is one of the applications that you have roof truss members over here, you have joints, you have these purlins, and then on top of that, you have this roofing tile. Another application is road and rail bridges. And the third example could be in stadiums where you have very large spans where you would use the primary trusses and secondary trusses to support the loading without any vertical structures, and to support very large roofs, you need trusses. Trusses are formed with pin or hinge joint to all internal members. The key thing to remember here is when we have pins, it means that they allow rotation. So when rotation is allowed, moment cannot develop. And the members are designed to carry only axial forces. This means that it can only develop tension and compression, where you can think of tension as if you try to stretch something, that is tension, and if you try to squash something or compress something, that is compression. How do we denote this tension and compression? We denote tension by arrows pointing away from the joint. An arrow pointing towards a joint would indicate compression. Here you might be thinking, okay, then how do we know the direction of arrows? So my answer would be, okay, initially assume that everything is in tension. When you work out the calculations, if the calculations work out to be negative, that means that the direction will be reversed. Members forming a pin jointed frame of a truss will not carry any loading perpendicular to their length. So no bending moment will be induced in the members. It means that all loads are applied at the joints. Loading is not going to be applied along the length of the member. So I cannot apply any UDL over here. So the first thing is joints are pinned. Second thing is loads are applied only at joints. And third thing is that trusses, they use triangulation to transfer loading. Now the method that we are going to use is method of joints. This method consists of isolating each joint of the frame and ensuring all applied and member forces at the joint are in equilibrium. What does it mean by equilibrium? It means that we will sum all forces in horizontal direction, we will sum all forces in vertical direction. And then we have to start the analysis at a joint with only two unknowns. If there are more than two unknowns, then certainly you cannot start with that joint. Thirdly, move from the joint to the joint using results from the previous calculation to reduce the number of unknown forces. Then you can find out the member forces and then draw a free body diagram for each joint, marking all applied forces and member force. Then we have to draw the free body diagram. Your initial assumption could be that all members are in tension. So some of the results will give you a negative answer, which means that our initial assumption was wrong. So if you assume initially that everything is in tension, if your answer comes out to be negative, the direction has to be reversed, which means that it is not in tension. Instead, it is in compression. So in that way, you'll be able to tell if a member is in tension or compression. Make sure that whatever sign convention that you're using, it has to be same throughout. Then these are the steps for the analysis. The first step is to work out the reactions at supports. The next step is to start at a joint with only two unknowns. If there are more unknowns, then certainly you cannot solve it. And then draw a free body diagram of the joint. The fourth step is mark the free body diagram, all applied forces and components, and then proceed clockwise around the joints, summing all the vertical forces and then all horizontal forces, which means that sum all vertical forces, sum all horizontal forces, and solve the equations in these steps 5 and 6. And the final step is to move to the next joint with unknown forces. Now in this example, firstly we have to work out the reactions at support A and B, and then we have to work out magnitude and direction of all member forces. Make it clear whether a member is in tension or compression, or the member is unloaded, means that it has zero force. First, we have to work out reactions. Support A is a pin support. It will have how many reactions? You have only two reactions, horizontal and vertical. And then I have one reaction at point B. Now, first of all, I would say summation of horizontal forces equal to 0. At the moment, the only horizontal force applied is this reaction, and there is no other horizontal force applied. So that is the reason horizontal reaction at A is 0. And the next thing for me would be to work out summation of moment. Here I have isolated the bottom portion over here because no other load is applied at any other part of the truss. Now we can take summation of moment for finding the equilibrium condition. The moment itself is not developing, which means that resisting moment is not developing, but we can certainly apply equilibrium equations to work out the forces. And summation of moment at A equal to 0 is a kind of equilibrium equation to work out the reactions in a truss. Now VA times 0 because there is no lever arm, HA times 0 because there is no lever arm, and then we have this force 40 kilonewton. The definition of moment is force times perpendicular distance. Force is 40 times perpendicular distance is 2. 40 times 2 will give me moment, and this is going in the same direction as clock, so that is the reason it is positive. So force times perpendicular distance, which is 2, and then we have VB, vertical reaction at B. Now this is creating, if I start from here, this is going in this direction, which is against the clock. That is the reason it is negative. So we have negative sign because of that. Now if you simplify this, you will get value of VB as 20 kilonewton. And then VB is 20 kilonewton. This means that VA will also be 20 kilonewton, but we will have to again use this summation of moment at B equal to 0. Now this will give us 20 kilonewton. Finding reactions here are obvious because we have a central point load applied. It looks like a simply supported beam, although it's a truss. It will be divided equally, which matches with our interpretation. And then we have to verify, and in this verification, you have to sum up all vertical forces. Upward forces are positive and downward forces are negative. So VA plus VB are positive, 40 is negative. This is giving us 0 vertical forces. It means that our answers were correct as well. Now, once I have these reactions, then I will put these reactions on the structure. Why did we find out reactions? Certainly, we needed these reactions. If I wanted to start with joint C, then joint C has so many forces. It has 5 unknown forces. It means that I cannot solve this. And the reason is that if the unknown forces are more than 2, then you can't really solve it. And on the other hand, if I move to other joints, F, E, and B, you have unknown forces more than 2. If I start with joint B, then now I have worked out reaction. There will be force in BF and there will be force in BC. Now this means that I have 2 unknown forces, which indicates to me that I can start with this joint, or I could start with joint A as well, where I have 2 unknown forces, where HA is equal to 0, and the choice is up to me. What I cannot start is joint C, where you have 5 unknown forces, D, where you have 3 unknown forces, E, where you have 3 unknown forces, F, where you have 3 unknown forces. Up to now, what I've done is that I've only found out reactions. Then calculation of internal forces. You can start with joint B or joint A. Here I have started with joint A, and then I have isolated joint A. Certainly my initial assumption is that all joints are in tension. For all the joints, the member forces are pointing away from the joint. Arrows pointing away from the joint indicate tension. I will start with joint A. Forces moving towards right are positive. Forces moving upwards are positive. This is my sign convention. Now, if you have a look at joint A, I have 3 forces. One is my vertical force, other is force in AD, third is force in AC. So if you see these directions, I have force AC moving rightwards, I have force AD moving upwards, and I will simply isolate this part. When you isolate this part, it will look like this: force in AD, force in AC, and upward vertical force. Apply equilibrium equation. First, summation of horizontal forces equal to 0. How many horizontal forces are here in this joint?
1.
1. What is the name of that? This one, FAC. And where is it pointing to? It's pointing towards right. Now this means that this is positive. Although I have HA over here as well, but HA is 0. So that's why I've added nothing here. So FAC plus 0, this is giving me force in AC equal to 0. And then my next step would be summation of vertical forces equal to 0. How many vertical forces are acting on this joint?
2.
2. And are they pointing upwards or downwards? Both of them are pointing upwards. If I compare it with this global axis direction, if I see VA is upwards, FAD is pointing upwards as well. That's the reason I will simply add them up. So VA plus FAD is equal to 0. So this is the equation that I will write. If you bring this VA on the other side of 0, that will give you a negative direction. It means that my assumption was incorrect. My assumption that this is going to be in tension is incorrect. FAD is going to be in compression. You can see that at joint A, now I know VA and I know FAC, this horizontal force, which is coming out to be 0. And I know FAD, which is minus 20. And this makes sense for me as well, doesn't it? The reason is that if vertical force is pointing upwards, which is reaction, there should be something which should balance it. And in order to balance it, it has to be downwards. So this arrow has to be downward so that forces are balanced over here. And this makes sense that 20 kilonewton is negative. So physically looking at it, you can see that VA is vertical and FAD, the other vertical force, has to be equal and opposite for it to be in equilibrium. So now these two forces are known, FAD and FAC. I can solve this joint D. Now at joint D, I have three forces. One is FAD. The value of FAD was negative. I have FDE, which is horizontal force, and then I have this inclined force, FDC. Summation of vertical forces equal to 0. And then if you sum up these vertical forces, I have FAD and then I have FDC. The angle between them is 45, and then I have this FDC cos 45. Because this angle is not with the horizontal, so that's why the vertical component is cos 45. If I sum this up, if I bring FDC on the other side, then it will give me FAD over cos 45. Now value of FAD is minus 20. Here you will follow the same direction as you have initially assumed. You will not change the direction as a result of your calculations, because we found out that FAD has to be in compression, but we will not change it at the moment. We will change it at the end. And in that way, value of FAD is negative 20. This negative comes from when we rearrange, it will lead to value of FDC, which is inclined, as 28.28 kilonewton. And then we have summation of horizontal forces equal to 0. Because here we are taking this angle with the vertical, so that's why this horizontal is sine 45. So Fx is equal to 0. This means that horizontal forces, now I have this horizontal force, FDE, which is pointing towards in the same direction as my global axis, which is pointing positive, pointing rightwards. And then you have the horizontal component of this FDC. The horizontal component is going to be FDC sine 45. And then if you put these values, if you bring FDC sine 45 on the other side of the equation, it turns to be in negative. And then simply you put value of FDC here. This will give you value of FDE. Now FDE is negative 20. So I found out this 28.28 and negative 20. So next I will go to joint E, because now I have FDE, which is known. You can first of all say summation of horizontal forces equal to 0. FEF is in the same direction as my sign convention. So it means that FEF has to be positive. And FDE, on the other hand, is in the opposite direction of my sign convention. Then I will say negative FDE. So FEF is equal to positive FDE. Now you might be wondering why then we have this negative, because the value of FDE is negative 20. And then here it's very interesting. This is one of the questions in some of the interviews as well, and also it's very useful. So Fy, now summation of Fy. Now here you can see that there is no vertical force applied except FEC. Summation of vertical force is equal to 0. This is negative FEC because it is against the direction of positive y-axis. FEC is 0 kilonewton. It means that it is not taking any load at all. FEF is negative 20. FEC is 0. Now this is really very important. So if you have a situation where you have a truss where you don't have any inclined members and only one vertical member is connected, then that will have zero force. That member is a redundant member. The member is there for structural integrity of the structure. Then I will move to joint B. At joint B, I have this reaction. I have vertical force BF, I have horizontal force BC. First, I will use summation of horizontal forces equal to 0. Horizontal forces means that I have FBC equal to 0. I have this vertical force, which is FBF, summation of vertical forces equal to 0. My both forces, the reaction and the force itself, they are pointing upwards, which means that both of them are positive. This will give me negative value. So let me move to joint F now. I have three members connected. F was the corner point towards right. You have FEF and you have FBF. I think both of them are known. FC is not known. So if I say summation of vertical forces equal to 0, FBF, which is acting downwards, which is against the positive direction, and then FFC cos theta, that is the vertical component. And this is downwards as well. If you bring the forces on the other side, then it will result in FBF over cos 45. And if you put value of FBF, which is negative 20, so negative multiplied with negative will give you positive, and FBC is going to be 28.28. Now again, we can use this joint C for verification of equilibrium. Joint C has got 5 forces connected and it has got 1 vertical load applied. So I will start with summation of horizontal forces equal to 0. Now if you put all the values of these, then you will get 0. This means that whatever you've done makes sense. Similarly, for Y, you should get 0. Once you have got all the forces, simply the forces which are in negative direction, simply reverse the direction of arrows. So you can see that member AD is in compression because force in member AD is negative. Have a look at direction of these arrows. You can see that now they are pointing towards the joint. Okay, so pointing towards the joint means that they are in compression. Again, our member DE is in compression because the value came out to be negative. And then EF and BF in compression, and members CD and CF are in tension. That's why you have arrows pointing away from the joint. And we have member AC, CB, which had 0 load, so that's why there is no arrow. I can say that member AC, BC, and CE are unloaded members. No load is being transferred in these 3 members.
Thanks for watching this lecture today. Click on left side of the screen to watch another video relevant to this lecture. Click on right screen to watch full playlist on structural mechanics.